Hello and welcome back. In this segment, we will talk about public key encryption. And as a supplementary read, I recommend Katz-Lindell, Chapter 11.1, Chapter 11.2.1, and 11.4.1. Last time, we've talked about key exchange protocols, but we've seen that key exchange requires interaction. So if Alice and Bob want to talk in private with one another, they first have to exchange a key via a key exchange protocol. Now, if you want to send a mail to someone, you don't want to interact with him first. So you just want to send your encrypted letter without asking the person you want to send this letter to first if they want to receive your letter. Okay, so in private key encryption, we use the same key K to encrypt and decrypt. Now, in public key encryption, we will have two distinct keys. We'll have a dedicated public key, PK, which can be used to encrypt. So the receiver will have a public key and publish this key. So you make it public through some channels, say you put it into a key database or you put it onto your website, you put it in a place where people can find it. Now, anyone can use this public key to encrypt the message and send it to you. And you will use your corresponding secret key, SK, to decrypt. Now let's make this a bit more formal. A public key encryption scheme consists of three PPT algorithms, keygen, enc, and dec, just like a private key encryption scheme, but with the following syntax now. Keygen is a randomized algorithm which takes as input the security parameter encoded in unary and outputs a pair of public and secret keys, PK and SK. The encryption algorithm, enc, takes as input a public key PK and a message M and outputs a ciphertext C. Of course, we allow enc to be a randomized algorithm as well. We'll discuss this later in more detail. The decryption algorithm dec takes as input a secret key SK, a ciphertext, and a ciphertext C, and outputs a message M. And dec we generally assume to be a deterministic algorithm. Now, as always, we will require encryption schemes, therefore also public key encryption schemes, to be correct. That is, it holds for all security parameters in N and all messages M in the corresponding message space. I didn't define the message space explicitly here, but the message space as well as the ciphertext space will always be somewhat implicit in the constructions that we will look at. So correctness requires that it holds for all security parameters and all messages, that the probability that if we first encrypt the message M using a public key PK and then decrypt the resulting ciphertext with a secret key SK, we obtain the same message M with probability 1, where this probability goes over the random choice of public key and secret key as well as the random coins used by the encryption algorithm enc. Historically, the first proposal of a public key encryption scheme is due to Revest, Shamir, and Edelman, who proposed such a scheme in 1978. And you've already seen the basics of this scheme, but let's briefly reiterate how this works. So in modern literature, we typically refer to this scheme as textbook RSA or plain RSA for reasons that we'll discuss in a moment. We typically don't refer to this as RSA encryption, just the textbook RSA scheme or the plain RSA scheme. How does key generation work? So first we choose to random security parameter bit primes. Think about security parameter here as something like 2000 or 1024 or 2048, this order of magnitude. So we choose two primes P and Q, and we set n to be the product of P and Q. Now we choose a random E modulo phi of n, and recall that the Euler's phi function, phi of n, for an n of this form is just p minus 1 times q minus 1. Where also recall phi of n is just the order of the multiplicative group Zn est. Okay. Now we choose ourselves a random E modulo phi of n such that GCD of E and phi of n is 1. And we'll compute, once we have such an E, we can compute a D or a D modulo phi of n such that E times D is 1 modulo phi of n. Our public key will be n and E, and the secret key will be n and D. How do we compute such a D? So here, this is done using the so-called extended Euclid-Lagrange-Berlekamp algorithm, or also ALBA algorithm. This is just like the standard GCD algorithm that you know, but it when we compute such a GCD, compute GCD of A and B, let's say this is C, then this algorithm will additionally output some x and y such that, some integers x and y such that x times A plus y times B equals C. Right, and if we do this for E and phi of n, then we will have, now we'll call this D instead of x, then we will have D times E plus, let's call it B times phi of n equals 1. And now if we reduce both sides modulo phi of n, we get that D times E is congruent 1 modulo phi of n. Okay. But this really just as a quick reiteration, I refer you to the last 3 lectures regarding the algebra and number theory. Now, how does encryption work? To encrypt a message M in Zn, we just compute a ciphertext C as M to the E modulo n. To decrypt a ciphertext C given a secret key n comma D, we just compute C to the D mod n. And how can we briefly see that this is correct? Well, if we have enc pk, let's say, make some more space, decrypt sk of encrypt pk of m, well, if we write it out, this is just m to the E times D modulo n. Or I've already simplified these two encryption operations into a single exponentiation. But now we know that D times E is congruent 1 modulo phi of n. So this is the same as m to the 1 plus, let's call it B times phi of n modulo n, which is just m times m to the B times phi of n modulo n modulo n. But we know that in this ring Zn, if we exponentiate with phi of n, that was the theorem of Fermat, right? We just get 1. Or, yes, this is just equals 1. Okay, if we're in this group, in the multiplicative group of units. But okay, so much for a quick reiteration of the textbook RSA scheme. Now let's consider if this is regarding or according to what we've seen already about encryption schemes, if this is a good encryption scheme. As you might imagine, there's sort of many problems with textbook RSA when we want to use it as an encryption scheme. First and foremost, of course, encryption in this scheme is deterministic, and that, as we've seen before, spells trouble. Why? Well, if encryption is deterministic, we can actually test whether a ciphertext C encrypts a certain message M by just testing whether this C is the same as enc pk of M. So this is kind of the biggest problem with this textbook RSA construction, but we'll see how this can be fixed in a later lecture. But there's also some other problems, maybe also features with this textbook RSA, which I'll just glance over real quickly. If you give me a ciphertext C which encrypts a message M, I can just compute 2 to the E, recall E is in the public key, 2 to the E times ciphertext C, and this will be an encryption of the message 2M. So in this basic scheme, I can translate I can convert an encryption of a message M into an encryption of a message of a different message 2M, right? Why is this the case? Let's quickly look at this. So this ciphertext C is just message to the E. I'm going to leave the modulo n away. So 2 to the E times C is just 2 to the E times M to the E. M to the E, which is of course 2M to the E, which is an encryption of the message 2M. Now, in some cases, this might be a problem, but in other cases, this might actually be a feature of this construction. But we're not going to go into that now. We will return to this at some later point. So let's go about defining security for public key encryption. And as a matter of fact, we will define a notion called in-CPA security for public key encryption analogously to the notion of in-CPA security for private key encryption, where recall in-CPA stands for indistinguishability under chosen plaintext attacks. Now, of course, we need to account for the fact that the public key PK in a public key encryption scheme is public. So we will have to additionally provide the public key PK as input to the adversary. But this also has an additional side effect or a side bonus. We won't have to provide the adversary A an encryption oracle. Why? Well, now the adversary A can just simulate an encryption oracle by itself by just using the public key, which makes the security definition in fact a little bit simpler as the in-CPA security definition for private key encryption. So, as always, we define this via an experiment. And how does the in-CPA experiment look for the case of public key encryption? Now, let's take our let's take a PPT adversary A and a challenger. Of course, first the challenger generates a pair of public and secret keys, PK and SK, and now gives the public key to the adversary. Adversary does whatever, some computation, and comes up with two messages M0 and M1 in the plaintext space corresponding to this public key. Challenger flips a random bit B and encrypts the message MB, resulting in a challenge ciphertext C asked, and it's gonna give C asked to the adversary. Now the adversary's task is to guess a bit B prime, and of course we say that the adversary wins if B prime equals B, then the challenger will output 1, otherwise 0, and we'll call this random variable, which denotes the output of this experiment, the output of the challenger in this experiment, just as int CPA A of security parameter. And of course, now the security definition with respect to this experiment is, we say in encryption scheme keygen and DEC is int CPA secure or has indistinguishable ciphertexts under chosen plaintext attacks if it holds for every PPT adversary A that there is a negligible function nu such that for all security parameters it holds that probability that the adversary wins the int CPA experiment, or probability that int CPA of index A of security parameter outputs 1 is at most 1 half plus nu of security parameter. Now that we have a security definition or a security notion for public key encryption, let's look at an encryption scheme which satisfies this security definition. In fact, we will construct an encryption scheme based on the simple Diffie-Hellman key exchange. And this was, in fact, just the observation of El Gamal back in the 80s, that essentially the Diffie-Hellman key exchange protocol can kind of be recast as a public key encryption scheme. So how do we do this? The El Gamal encryption scheme, keygen and DEC, is provided as follows. So what does keygen do? First, we generate a cryptographic group G of prime order P, where P is roughly of size 2 to the security parameter, and with a generator G, right? This generator lowercase g generates our group capital G. Now we will choose an X in ZP uniformly at random and set H to G to the X. And we will output as public key the pair G, H, and as secret key we will keep X. Now we will implicitly assume that the public key includes the description of the group G and the group order P. Often in practice, people use, in fact, a fixed group. So their key generation doesn't generate a new group every time you run the keygen algorithm, but just runs everything from here downwards. So there the group is often fixed. But there are good reasons to maybe argue that the group should be chosen at random, but we're not going to discuss this now. Just keep this in mind that in some specifications the group is freshly generated, but in most standardized specifications the group G is fixed. Okay, so much for keygen. What does encryption do? Encryption takes the public key consisting of the two group elements G and H and a message M. And this message M will be in the group, so this group G will also be our message space. Now choose a random Y in ZP and compute the ciphertext G to the Y and H to the Y times M. Decryption takes as input the secret key SK and a ciphertext C1 and C2, and it computes and outputs a message M as C2 times C1 to the minus X. So I said that this is essentially a direct construction from the Diffie-Hellman key exchange protocol. Why is that so? Well, if we look at the keygen algorithm, this does essentially the same as the algorithm Alice 1 that we've seen in the last lecture, right? Where the public key is just a message that's being sent from Alice to Bob, and the secret key, which could also include the group G, but we omit that here, is the private state of Alice, or what she keeps in her head. Now, encryption just runs the algorithm of Bob, right? Remember, Bob sends this G to the Y to Alice and computes a key K as H to the Y. But now, in this Elgamal encryption scheme, Bob just directly uses this key K as a one-time pad to multiply onto the message M. Recall that when we discussed the one-time pad, we discussed that this works in any group. Now here we have a group, so once we have a group element, I mean, we will still have to show that it's not really a one-time pad, but we use it like a one-time pad. We essentially, if this H to the Y was a random value, then H to the Y times M would be a one-time pad encryption of the message M. So that's really the only thing happening here. Bob computes directly the key and uses it sort of like a one-time pad. What does Alice do? Well, this is essentially the same as the Bob algorithm. And now, of course, the last step is similar to Alice 2. What does she do? Well, she computes this C2 times C1 to the minus X, where essentially computing this C1 to the X is what the Alice 2 algorithm does. But let's look at this on the next slide when we consider correctness of this scheme. So let's say C1, C2 is an encryption under public PK of a message M. Then of course it holds that C1, where maybe let me specify the public key, where PK is G comma H, and H is of course G to the X. Our SK is X. Then it holds that C1 is just G to the Y, and C2 is H to the Y times M. Now, if we decrypt using our secret key, which is X, this ciphertext C1, C2, well, this is just C2 times C1 to the minus X. But now let's just plug in C2 and C1. C2 is H to the Y times M times, well, what is C1 to the minus X? This is just G to the Y to the minus X. Now let's plug in this H. And we get that this is G to the XY times M times G to the minus xy. Of course, now these two here cancel out. The second one is a multiplicative inverse, or the inverse group element of the first one, and we get that this gives us back the message M. Now for the interesting part, namely establishing INCPA security. So assume that the DDH assumption holds in the group G, then the Elgamal encryption scheme keygen and DEC is INCPA secure. So let's get right into the proof of the theorem. As always, assume towards contradiction. That there is a PPT adversary A, which breaks the INCPA security of the Elgamal encryption scheme with non-negligible advantage epsilon. So there exists a PPT adversary A and a non-negligible epsilon such that probability that our adversary A wins the INCPA experiment is greater than 1/2, greater equal 1/2 plus epsilon. Now, of course, we will have to show that this leads to a contradiction against the DDH assumption. So what we will show is this implies a PPT distinguisher D against DDH, contradicting the DDH assumption. Okay. But as always, let's first write down the security experiment, the INCPA experiment with our adversary A and the Elgamal encryption scheme. So for simplicity, I'll just call our INCPA experiment exp now. See, of course, in a moment why I'm gonna do this. Here we have our adversary. Here we'll have our adversary A. And here the challenger. So what does the challenger do? Now first, of course, it computes a public key and a corresponding secret key as G, G to the X. The secret key is just X, but as it turns out, we don't really need the secret key. If you look at the definition of the INCPA experiment, the secret key is never needed. So we give this public key PK to the adversary A. Right? I can maybe write that X is chosen uniformly random from ZP. Okay, now adversary gets the public key, chooses two messages M0 and M1. The challenger flips a random bit B, chooses B uniformly at random from 0, 1, and encrypts the message MB. How do we encrypt the message MB? Well, first we choose a Y uniformly random from ZP. Then we say C1, or we compute C1 as G to the Y and C2 as H to the Y, or where this is H, h to the y times mb. This is C ast. And we give this C ast to the adversary. Whereupon, of course, the adversary outputs a bit B prime, and the challenger announces win or output 1, whatever, if B prime equals B, otherwise lose. Where with win we just mean that the challenger outputs 1 and lose he outputs 0. Okay, this is the INCPA experiment. Now, as we typically do in these security proofs, we consider a slight modification of this security experiment, a thought experiment, or more likely hybrid experiment if you want so. We'll just briefly modify this experiment into an experiment X prime. And all I'm going to change is I'm going to replace this h to the y just with an element g to the r, where r is chosen uniformly random from ZP. Now, I've already alluded to earlier that essentially this this ciphertext, I'm seeing that there's a small writing mistake here. This is, of course, the thing is, of course, called C2, and C as consists of C1, C2. But okay, as I've already alluded to earlier, the way C2 is computed is pretty much like a one-time pad encryption in the group G. And now what I've done with this modification of this experiment is now C2 actually is a one-time pad encryption. So in the original INCPA experiment, it just looked like a one-time pad encryption, but now it actually is a one-time pad encryption. Why? Well, this R that I'm computing here, this is never used anywhere else, right? This is independent of the public key and of C1. So this is a truly random string. So that means G to the R is uniform in the group G. But that really just means that this ciphertext C ast now just consists of two uniformly random group elements, or just using the security of the one-time pad in arbitrary groups or in arbitrary finite groups. We can immediately argue that the winning probability of A in this modified experiment X prime is exactly 1/2, since one-time pad is perfectly secure. That's the guarantee that we get. So we get that the probability that X prime outputs 1 is exactly 1/2, thanks to the security of the one-time pad. Okay. And now we will use this fact that the adversary A has an advantage against the INCPA experiment, or the experiment X, but no advantage against the experiment X prime, to construct a PPT distinguisher D against the DDH problem. So we'll construct PPT distinguisher D against DDH. How do we do this? Well, our distinguisher, let's make him big, does the following. Now, of course, he will simulate these experiments. So as input, recall, he just gets 4 group elements. Call the first one G, H, call it G prime and H prime. We've discussed this in the last lecture. So in the DDH problem, you're being given 4 group elements, and you have to decide whether they're of which form they are. But we'll do that on the next slide. So okay, what does D do? Now, of course, D will simulate the INCPA or EXP experiment with a small modification. First, it will set the public key just to GH, where of course it obtains G and H from its own input. It gives this public key to the adversary. And of course, whereupon the adversary outputs 2 messages M0, M1. Next, chooses a random bit B and sets the ciphertext C1 part to G prime. So here we're going to use G prime. And the ciphertext part C2, we're going to set to H prime times MB, right? And of course, this H prime also comes from here, from the distinguisher's own input. And now it gives the challenge ciphertext C asked, which is C1, C2, to the adversary, whereupon the adversary outputs a bit B, and we say output our distinguisher D now outputs 1 if B prime equals B, otherwise 0. Okay, this is our distinguisher D. Now we will have to argue that this distinguisher, in fact, has an advantage against the DDH problem. To do this, let's of course again distinguish cases. Case 1. In case 1, the input GH G prime H prime is of the form G comma G to the X, G to the Y, G to the X, Y. This was kind of the first distribution in the DDH problem, kind of a transcript of the DDH key exchange protocol. So what happens in this case? Now, in this case, we can argue that in this case D faithfully simulates the INCPA experiment. Simulates the INCPA experiment. Why is this the case? Well, in this case, we will have that C equals, or C1 equals G to the Y, and C2 equals H to the, or let's call it G to the XY times MB. But of course, this is, H will be G to the X. This will just be H to the Y times MB, right? In such a DDH tuple, of course, X, Y are chosen uniformly random from ZP. So in this case, if the input of the distinguisher was of this form G to the X, G to the Y, G to the XY, then our distinguisher faithfully simulates the INCPA experiment. That is, both the public key and the challenge ciphertext have the correct distribution or the same distribution as in the INCPA experiment. So we will get that probability that our distinguisher D on input G, G to the X, G to the Y, G to the XY outputs 1 is really just the same as probability that our adversary A wins the INCPA experiment, which we know is greater than 1/2 plus epsilon. Okay, now what's case 2? Now in case 2, of course, the input of our distinguisher G prime, H prime is of the form G, G to the X, G to the Y, and G to the R, where X, Y, R are chosen uniformly random from ZP, right? So G is a generator here, and the other 3 group elements, G to the X, G to Y, G to R, are just uniformly random in this group. Now, of course, as you expected, in this case, D faithfully simulates the experiment X prime. Case D faithfully simulates X prime, the modified experiment. That is, probability that D on input G, G to the X, G to the Y, G to the R outputs 1 is, of course, the same as probability X prime equals 1. But we've seen that by the security of the one-time pad, this is exactly 1/2. Now that we have these 2 cases, we can compute the distinguishing advantage of D, and we will get, let's maybe do this on a new slide, we get that probability that D on input a DDH tuple, G to the X to the Y, G to the XY outputs 1 minus probability D of G, G to the X, G to the Y, G to the R. This is an R outputs 1 is greater than, well, 1/2 plus epsilon minus 1/2, which is of course epsilon. And this is non-negligible. Now, of course, this is the desired contradiction that we have against the DDH assumption, right? Now we have that D distinguishes DDH problem with advantage epsilon. This is, of course, the desired contradiction, which concludes this proof. Now it's again time to wrap up this lecture. We've discussed that public key encryption allows for secure communication really without prior interaction. We've seen that the textbook RSA scheme, which was the first proposal of a public key encryption scheme, is not a secure public key encryption scheme by modern standards, by the modern security definition of INCPA security. However, as it will turn out, it is a useful building block for more complex constructions of encryption schemes. So the standard security notion of public key encryption is also called INCPA security. Indistinguishability under chosen plaintext attacks, just as in the private key setting. And we've adapted the security notion from the private key definition. Historically, I must say, it was actually vice versa. Historically, we first had the INCPA security definition for public key encryption, and then sort of derived the INCPA security notion for private key encryption from that. So even though it makes sense to teach this first, or to first teach the INCPA security notion for private key encryption, really in terms of historical development, we first had this security notion for public key encryption. And finally, we've seen that the El-Gamal encryption scheme, which we've constructed around the Diffie-Hellman key exchange, is INCPA secure under the decisional Diffie-Hellman problem. That's all for today. Thanks, and until next time.